And then we're going to point to the top and to the bottom. The reason we're going to do that is if we fold down the top and the bottom, that's going to give us pH. Okay, so that's why we're pointing to the top and the bottom. And then next to that, we're going to put the formula log of the concentration of pH. Or sorry, log of the concentration of hydrogen. All right, so that's the main thing that you need to do today. Now, the other place you can go from hydronium is to get to the concentration of hydroxide. So to do that, we're going to pull to the inside. So I have an arrow here pointing to the inside, and it's Kw over this concentration. Okay, so if I open up from the inside, that's what I get if I do Kw over the concentration of H3O plus. If you want, you can write the value of that. What is Kw? Remember? 10 to the minus 14. So that might be helpful to write down too. Just put 10 to the minus 14 over H3O plus. And so that would give us hydroxide. So similarly with hydroxide, I can do the same things that I did with pH, only for hydroxide. So I can go backwards. 10 to the minus 14 over OH would give me the concentration of hydronium. And if I go to the inside, I can do negative log of OH to get the pH. Okay. So that's all we're going to worry about for right now. There are a handful of these floating around. Is there anybody who is at a table that doesn't have them? Okay, I have these two. Right. I am wearing a mask today because I have a really bad sore throat. So after you guys get started on your quiz, I'm going to have Roxy come in and proctor the quiz. So I told her you're allowed to use these flippy doodles if they help you. You, of course, can use a calculator. Since one of the questions is an ice problem involving acids and bases, I thought I'd start there to give us a little bit more practice on that. Go to the Now, whenever you have a weak acid, you need to do the ice table. And it's not going to say initially, or this much was put in the jar. So the concentration on the jar, or the concentration that they give you in the problem, that's going to be your initial concentration. And let's see. Things for my online people. So we are also given the Ka, and remember Ka is found the way every other K is found. We're going to do products minus reactants. Okay, so we're going to have to use that later on. So there's the expression for Ka. Now notice that this is a diprotic acid. There are two hydrogens out front. Okay, so ultimately, this acid can lose both of them, but it's going to do it one at a time. It's going to lose almost all of that first one before we get around to losing any of the second. That's not what I want. All right, so if we start with a 0.15 molar solution of this, and we want to know what is the equilibrium concentration of H3O plus, we're going to have our reaction here. Now, if there's not a reaction given, I have given it to you on the quiz, but if there's not a reaction given, what you're going to do is put the weak acid and water as the reactants. And we know that acids are proton donors or hydrogen donors. So the products are going to look like the weak acid with one less hydrogen and the water with one more hydrogen, the hydronium ion. All right, so what is going to go for the initial for the H2CO3? Yeah, the H2CO3, yes. So the concentration they give you is that very first one. We put that in there. Why am I putting zeros for the products? they're products, so we don't usually start with products. So unless they tell me that they're in there, we're going to leave those out. Okay, so it's 0 for those. Now, what's the C line? What do I do with C? The X's, okay? Reactants are going down, so it's minus X. Products are going up, so it's plus X. And then we add those two together. So we have 0.15 minus X, X, and X. So we're going to plug these into the equilibrium expression. There's our equilibrium expression. So try that out yourself. See if you can figure out how to plug it in. And remember, the Ka was given to us in the problem. Okay, so we're going to plug in the Ka on the other side because we can't solve for X if we don't have an equal sign in there. So we need to have that. All right. What are we going to do about this guy here, this little X? That's going to be problematic when we start distributing everything. We can ignore it, okay? How do we know we can ignore it? Well, it's probably a lot smaller than this, but we're going to check our Ka value. If this is a smaller number than 10 to the minus 3, so 10 to the minus 4 or something else, then we can ignore it. Okay, that's my general rule of thumb. But remember that the bigger this negative number gets, the smaller the overall number. All right, so what are we going to do next? We got to multiply that number on the bottom, the 0.15, over there. I get 6.6 times 10 to the minus 8. All right, so now what do I need to do? I have to do the square root. Now we've solved for X. We have to go back to the original question and ask ourselves, did we answer the question? So I'm going to have to go backwards in the slides. So it says, what is the equilibrium concentration of H3O plus? Is that what X is? Yes. Okay. So notice that when we see what X was, I put equals H3O plus. I'd like you to do that on your tests and quizzes so that I know you found what was asked for. Tell me what H3O plus is equal to. So we're going to ask ourselves, was it a fair assumption that this was really small and wouldn't affect the 0.15? Well, if we compare the two, that 0.00026 is so much smaller than the 0.15, it wouldn't have affected it at all. So that was a fair assumption. All right, so generally, this is going to be a reasonable approximation for problems that I give you. So what you're going to find as you do several of these is that you can really just get down to the concentration of H3O plus is going to be the square root of the original concentration times Ka. That's the math you end up doing altogether. All right. Questions on that? We wanted to find the pH of this. If you have one of these white calculators, what was it, 6.6 times 10 to the minus 8? The first thing you have to do is plug in the concentration, the concentration. The 6.6 times 10 on this calculator, it says XY. That's how you do an exponent. You're going to put in the 8 first and then the minus. If you do the minus first, it's going to say to the minus 10 instead of minus 8. And then hit enter. So you should see the first part here and the exponent on the 10 up here. Okay. Then you want the negative log of that. So you're going to find the log button, which is here at the top on this calculator. And then hit the negative button. So this is 7.18. Sig figs are a little bit wonky when we have logs. So as a general rule, just carry 2 numbers past the decimal point when you're finding a pH or a pOH. Okay. Now, what if you have one of these calculators? This is more like a graphic calculation. So I would plug things in how it normally goes. So I've got a minus sign down at the bottom. Well, first I have to turn it on. But in minus, then I find my log. Then I put my 6.6 And you can either type out times 10 to the, or you can use that EE that's right there, 10 to the -8. And I get 7.1 on this one as well. So we're going to look at relative strengths of acids and bases. So we talked about this a little bit. We have strong acids and strong bases. Good to know what they are. I'm going to ask you to identify some strong acids on your quiz. So make sure you know some of those. Let's see. For weak acids, the difference is they only partially dissociate, whereas strong acids completely dissociate. So for weak acids, equilibrium applies. Strong acids don't have a Ka because it would be basically infinite. Weak acids have a Ka. Weak bases have a Kb, and it's found in a similar way. We'll talk about bases Friday. Okay, remember from our Bronsted-Lowry definition that our acids and bases are defined by the proton transfer. So the acid gives up the proton and the base gains the proton. This means that we can find the other side of the equation by just looking at the same formula with one less hydrogen or one more hydrogen. All right, so this was our particulate view of what happens where we move a hydrogen from the acid to the base. And I'm going to skip through that. I'm going to look at conjugate pairs. So acids and bases come in what we call conjugate pairs. The conjugate pairs look like each other with the exception of a hydrogen. So if I look at CH3COOH on the reactant side, its pair or its partner, its conjugate, is on the product side and is the same thing missing an H. Does that make sense? So the conjugate of the water is going to be the hydrogen. All right. So let's think about Le Chatelier for a moment. Oh, that's what I just said. So CH3COOH is an acid, and we say that CH3COO minus is its conjugate base. And then water is a base, and it's not a base because it has a basic pH. It's a base because it's accepting the proton. And but its conjugate acid is going to be H3O plus. All right, so on this reaction, the first line, we've got HF mixed with water. What is going to be the conjugate base of HF? Just F. But because hydrogen is positive, that means it's leaving behind an electron, so it's going to be F minus. All right. And then what's going to be the conjugate acid of the water? Yeah, H3O, and since that is a positively charged hydrogen, it'll be H3O plus. Anybody remember the name of that ion? Hydronium. Now, we have similar things going on with these other things. Remember I said with the Bronsted-Lowry, this frees us from having to do this in water. So we could have this reacting with different ions, even if there's water not around. But we're going to come back to those in just a minute. First, we're going to look at why we might consider the conjugate base a base. So let's look at this reaction again. Let's think about Le Chatelier. If I increase the CH3COO minus, now I can't have a bottle full of negative ions. They have to have something positive with them. So the way I'm going to increase those ions is with sodium acetate. So you see there at the top, it says sodium acetate. Sodium is a spectator ion. It's not going to do anything, okay? So we're going to increase that acetate. What does Le Chatelier say is going to happen to the shift? Which way is this going to move? Towards the reactants, okay? So as I move towards the reactants are going to increase and the other products are going to decrease. So how do we measure pH? By the concentration of this. So if the concentration of H3O plus is going down, it's less acidic. Okay, so this is why we consider that to be a base. Even if we never had acetic acid present and we just dissolved NCH3COO or sodium acetate in water, it would have a basic pH. Okay, now remember that because the hydronium and the hydroxide are in equilibrium with each other, as the hydronium goes down, the OH is going to rise. We're going to have more of that. And that's what we think of as being associated with our bases, is that hydroxide. All right, so that is why CH3COO or acetate is a base. And we can write that in the other direction by saying, let's just add that ion to water. And when we do, this is the reaction. Since OH is a product here, this is the reaction we would use to find Kb. So Ka will have hydronium as a product, Kb will have hydroxide as a product for our purposes. All right. Let's take a look at some of these others, see if we can identify conjugate acids and conjugate bases. All right, so our acid is HCOOH. What is its conjugate base going to be? HCOO minus, right? What is the conjugate acid of CN minus going to be? HCN. Okay, so if our base on the reactant side had a negative charge, it's going to be neutralized. Okay. Ammonium already has a positive charge. That's our acid. What is its conjugate base going to be? NH3 or ammonia, right? And so because it's taking the positive charge with it, the NH3 is going to be neutral. What about our CO3 2 minus? What is the conjugate acid going to be? HCO3 1 minus. All right. So we will go through the rest of these on Friday just to remind ourselves of how to do these things. I'm going to sanitize my hands for the 17th time today.